Music theory with OneNote. Hertz to notes, spectrum to circle. In other words, we're going to measure pitch in hertz, resulting in a spectrum similar to a number line going infinitely upwards. Also noting, however, that we perceive pitch to have a circular, repetitive quality. Therefore, we'd like to visualize a 3D shape related to pitch, similar to a staircase, having both a repetitive quality and a linear quality. We'll map that out, so get ready and some coffee, because although we're just playing with one note, it's a beautiful note. You're not required to, but if you have access to it and would like to follow along, we're currently in the OneNote file of Modal Node System, MNS Presentation 2001, OneNote, Hertz to notes, spectrum to circle, list of presentations, which we plan on adding plenty more to shortly. Also noting, within this OneNote presentation, we'll spend all of our time on the music theory side of things, but we have another similarly numbered and named presentation where we build these tables in Excel, practicing music, Excel, and just table visualization all at the same time. Our objective: to maximize the use of color to better understand music theory in general, better navigate the fretboard more specifically. This being an example of our fretboard, it's a little bit overwhelming with all the color. Noting in practice, we can often tone down the color by, instead of putting a color on all 7 notes of the collection of notes we're working on, only putting the color on those notes that we're specifically focused in on. Noting that the fretboard has the low or heavy E string, the one closest to the ceiling on top, only putting something in those cells that are part of the 7-note collection that we're focused in on. This one being focused in on the 7-note collection around the C major. We have within the cells the letter of the note, this being a G, 11, that's the number of the note, the Nashville number system number, which is basically a modal numbering system, the letter of the mode, this being Mixolydian, this being Locrian, this being the Ionian. This is what I would call position 1 shape here. We can want to see that shape in my theory as many ways as possible. So I'd like to be able to see it by shape. I'd like to be able to count it out by formula. I can also look at it with these squares and dots, because that's kind of like the even or odd numbers. Notice that the square happens on the even number. So if I was to count this out, it would be a square, 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 and then circle, 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 right? So you're going to get that pattern when you're applying the formula, whole, whole, half, whole, 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 half. And then, of course, we can also look at it by color, noting most people, when they use color, they just kind of use it randomly, right? We just pick a note like the C, we make all the C's green or something, and that helps us to focus in on it, which is great. But we can get way more formal with the colors, which is what we want to be doing here, actually assigning a color that's an absolute color, which will always be the same. So we'll always have this green when we're looking at it in this format for a C. Now you might say that's kind of arbitrary. Why would I assign the colors? Well, we're going to assign them in a way that kind of makes sense, because we're going to map on the color wheel to the pitch wheel, so that the distance between the colors is actually kind of analogous to the distance within the pitches. And that will actually give us patterns that will help us to better analyze from a color perspective. So we can actually go from here to here. This distance gives us an idea of that perfect fifth, because we can imagine they're going to be where they land on, in essence, a circle if we put this basically in a color wheel. Noting that this, going from this C to this G, is actually a perfect fifth, which is a very stable thing in music. But you might say that looks a little clashy from a color standpoint. So that's how the colors will often work, because it's often, from a pitch standpoint, it's the thing on the opposite side of the circle when you're in the 7-note collection, which is actually what you're looking for the more stable intervals, which it doesn't exactly tie into when you're painting something, because that would be more clashy when you paint. So notice that you have to kind of think about how the analogy is going to be working when we apply it to pitch. We'll talk more about that later. But I think it can really be useful to associate a specific color to each of the notes. So for example, here we have it on the C. If I move this up, now we have the same colors, but we're now in a different collection of notes. This is going to be the Ionian for the D major. We still have the A is going to be red over here. Now note, we also might say, hey, look, I would rather see the color system so that it's tied to the nodes, which is what we've talked about as continents in our analogy in prior presentations. And we can do that as well. So we're going to take this color scheme that we had up here and say, now I'm going to tie it not to the C, I'm going to tie it to the Ionian node, and keep that the same. So for example, here's the same thing, but this time it's the same colors, but it's tied to the Ionian node. When I move up to the key of D, now this whole shape moved up. So in this color scheme, we're not assigning a specific color to all of the notes, but rather assigning a specific color to the relative nodes, so we can see the shape basically move up. All right, and so we'll actually make an Excel worksheet that has the tools to apply that out, and I think that could be a highly useful way to visualize the fretboard, which is clearly utilized in practice most of the time. So to do that, I want to kind of map out the analogy by basically getting formal here. We're going to get into a little bit of math, but hopefully that'll get you the concept in terms of how is the shape of music, what does the shape of music look like, and then how can we map the color wheel onto it so that we get an analogous color system that's going to give us this ability to look at the fretboard and music theory in a more depth way. You know, the more angles we look at the same thing, the better we can understand it, is my theory. So that's going to be our idea. Now notice that the color and measuring something in color, the color wheel, which is measuring the length of light, is not exactly the same thing as measuring in hertz. Now, if you look on the internet and you look this stuff up, you've got a lot of interesting people that have good ideas about color, but a lot of times they say some things that are not quite correct as well, such as they'll say that the measurements of color are exactly the same as the measurements for sound, and you can map them onto each other, and it's one for one. In other words, it's kind of like, it almost gets mystical. They're like, our two senses are completely the same. We perceive pitch in exactly the same way as we perceive color by these spectrums that come out to the exact same measurements. That's not exactly right. That would be beautiful if it was the case, but that's not exactly the case, because pitch does have this repetitive nature to it. So when we measure pitch, we measure it by basically how many wavelengths happen in a time frame. So we count the wavelengths. Similarly, you can think of like a wave in an ocean, but it's actually compression waves. But it's usually nice to think about sine waves, like ocean waves. How many waves happen? So we can measure the waves. And that means it's always going to be a linear thing, because we're always going to say, okay, this is how many waves, and then the thing's going to go up. We call it hertz, right? So we're going to say if it's 440, then it's going to go up and up and up, and so on. So it's a linear progression. However, we have this doubling thing, and that's when the octave happens. So we perceive in our ears when it doubles, we have the perception of it doubling. That's where the circular nature to music comes in. So we measure it linearly, just like we would measure anything else. It's just going to keep on going up infinitely like a note number line, and there's a certain range that we can view or hear with our ears, right? And that's the audible range. But there's this weird phenomenon that it doubles, and we perceive it as doubling, which is great for humans and probably animals as well, like whales and stuff, because they sing, and the males and females have different octave of pitches. So we want to be able to sing, women and men sing different octaves, because that's where their vocal range is, and they can still sing together. That's pretty cool. Now, the color isn't the same. We measure those by the length of the light. So the length of the light still keeps on going up, right? So we say, oh, the light's getting longer or shorter, and it ends up in a range of the length of light, which we perceive as a color spectrum. So that's great, but it doesn't really have the same circular nature that's inherent to it, because we don't perceive, as the color keeps on getting longer, that it actually wraps around. It doesn't actually wrap around. It's just a spectrum, right? It goes just in a line. But we could force it into a circle, and that's quite common to do. So some of the systems of the color wheel have forced it into a circle, and they have actually fudged the end of it to kind of fade it back in. So we'll talk more about that when we get to the color side. But that works perfectly as an analogy. So I just want to point out it's not exactly the same. They forced the color to kind of work as an analogy. Now, also note that the color then is not going to have a spiral staircase format, even if I force it into a circle, because it's not going to have that repetitive kind of concept to it. So how can we add that 3D dimension? We can add another factor, which isn't hue. It isn't the length of the wavelength, but it'd be like lightness or brightness, meaning I can make it lighter or brighter, blending it with white or black, right? It's closer or further away from white or black. Again, that's not the same thing as pitch, because pitch is we're only measuring it with the one thing, how many wavelengths happen, and it only goes up, and it has this phenomenon of doubling. With hue or color, we measure the hue, which is the wavelength, but then we can add another factor to add in the 3D. It's not the wavelength we're measuring, but we can make it closer or lesser white or black, which is lightness or pitch. All right, that's the project. And so we'll end up then with color that will be analogous, that it's more formal. We can see why we derived it. We can see why we assigned a particular color to a particular pitch. And even if we want to represent things like an interval that is two pitches, I can take the average or the log average, which we'll talk about, or whatever, and that'll represent another color, right? It'll represent the average of those two pitches, and we can start to play with that as an analogy as well. All right, so let's first think about the hertz. So we usually start measuring hertz in 440. Now 440 is an A, so that's where we started the musical alphabet. Now if we get into octaves, we call it the octaves get messed up. We'll talk about that later. But because of the piano, for whatever reason, we picked the C as the thing we play in. So they call middle C C4, even though we started measuring the main distance that we play in from A. That gets wonky, right? But I'm gonna say that really what we should be thinking of it as is the 440, which is an A up to the G, is one octave, right? That's going to be the octave that we typically will work in within the collection of notes that we're most familiar with, all 12 notes, right? 12 notes within the collection started at 440 hertz. Now, if we just go hertz by hertz, then it would be 440. That would be the number of waves that we're visualizing. You can imagine ocean waves, but they're more like compression waves. But the number of waves that pass, and then we're just going one by one, hertz by hertz, going up. Now, obviously, in our musical alphabet, we only have 12 notes. So if I was to just go hertz by hertz and count from 440, which is an A, all the way up, how many waves do we get before we get to the end of it? Let's go all the way down and say it goes all the way down to 441 units later, we get to 880. Now, why are we stopping at 880? Because that's twice of 440. That's when this phenomenon in our eardrums is saying, hey, look, those are the same. That's what our ears are telling us. It's just if we play them together, they sound like the same thing. They sound unison. So that means that one octave has to be within 440 to 880. See, it has to fit in there because I need it, when we get to 880, I need it to repeat. So I need 880 to be an A. It's the next octave up of the A. So if we start at 440, the octave has to end at 880, the double of 440. So we have all of these all of these options then. So you can imagine different cultures picking different pitches that they're going to work with. But you can't really imagine, and I don't believe any culture has picked something that doesn't fit like within an octave, because men and women want to sing together basically in all cultures. So you can't really, there's some things that you can do, but you can't really pick something that's going to be totally out of whack. So in Western music, we picked 12. So we want to break this into 12 pitches, basically, is the general idea. This would be the doubling. Why did we pick 12? Well, it seems to fit fairly well. Maybe there's some cultural reasons. I don't know. There's 12 disciples and stuff. 12 seems to come up a lot. I don't know. 12 donuts. I don't know. But we picked 12, okay? So what you would think then is you'd say, okay, if I'm going to be picking, basically, that's not exactly right. We picked 12 because Pythagoras was doing it with ratios, and he picked a perfect fifth, and then he figured out the ratios, and then later on we kind of filled in the gap with this ratio conception. But it's easier to think from us now that we can measure in hertz. It's kind of nice to map out all the hertz, right, and then try to break it out evenly, break out an even breakout. So if we're going to have 12 crayons, 12 different colors within our pitch color format, what do they call it? Palette, our color palette, our pitch color palette. Then you would think you could take the 441 if they were measured in one at a time divided by 12, and you would think that I can just go up 36.75 waves, and I would get 12 pitches that are evenly spaced about. That would be equal spacing. That you would think that would work, but there's a problem when I go into the next octave up if I do it that way, because when I go from the last bit in this octave, I'm not going to go up 36.75 to get to the next one, because it's going to be out of whack, right? The distance is going to be out of whack. Why? Because we're visualizing it repeating, and when something repeats, it's like a circle. So we can't, if it was a circle, it needs 360 degrees, and this has 441 degrees. It's not even, right? So the repetitive process doesn't happen evenly if I just break this out like one by one. So that's the problem. This is the first thing you would think to do, but it's not exactly what we do, because it's not going to fit into a circle. But if we did it this way, we could say, all right, you'd say, if we start at 0, that'd be 440 hertz, and then we're going to say N is going to be at 0, 1, 2, 3, up to 12, and then we're going to put we can do our formula here. Let's first do it this way. So what would I do? I would go up 37. So I rounded this to 37, so that in Excel it's a little bit easier to find, because I don't find a 0.75 waves. We went one wave at a time. So if I start at 440 and then I go up 37 from 440 is going to get me to 437. So I'm going to go to 437, and then I'm going to go up another 37 plus 37 gives me to 71. So 70. So if I go up 71, that would be a 513. Meaning if I look for this 74 over here, 74 on the left-hand side, we get to 513 hertzes, right? So that we get to 513. If I go up 74 plus another 37, I get to 111. That would be the left-hand column, which would give me in hertzes 550. And if I go up 111 plus 37, I get to 148. And so this would be the hertzes. So you would think then, if I used even spacing, these hertzes would give us our 12 notes. You would think would be, our notes would be from 440 to 846 would be the notes A to G sharp. But that's not exactly what they are, and they're closer to something like this. And we do a formula in order to figure this out, and the formula looks like this. Now I don't want to get too into wonky on the formula, but we're going to be taking the 440, and we're going to say it's going to be times 2. That makes sense because it doubles when it doubles, that's when the octave happens. And then to the power of this 0 divided by 12. What this is doing is it's basically saying I have 12 degrees, and if I'm only looking at 12 notes, I want to bend it into a circle. So this is giving us a bended 12 note basically circle by taking the starting point here, and you can imagine like we're drawing a compass around it, right? We put the point of the compass in, and then we're drawing a circle around it that's going to have 12 points by doubling it to each point divided by 12, right? And so if we do this to each one, this one would be still the 440, but now the n would be 1 divided by 12. Okay, so I don't want to get too focused in on the math. Just the idea would be this is us more formally taking the 12 notes and bending them into a circle. So you have this difference between what you would normally get evenly to what we're doing. Why does that matter? Because if we did it this way, you're not going to get an even distance when you go up to the next octave, right? We want to get an even distance as we go around the circle again to go to the next octave. But although this works for the 12 notes, I want to have 360 notes that have all of that have all that in there. So I'd rather, why? Because what I'd like to be able to do is say, well, what if I want to map it onto the colors, and then I also can start to say, well, what if I took an average of 2 notes? If I took the average of 2 notes, I want to give me the log average that's going to still be like on the circle. So I don't want just 12 notes. I want to look at all 360 notes. So in other words, what I visualize this as taking like this list, which is 1 by 1, and it has 441. I want to squish it down to 360 by putting decimals and whatnot within it. I want 360 evenly spaced distances instead of 441, so that I can map that onto a 360 color wheel. Okay, so a circle, in other words, has 360 degrees. This goes down to 360 in the numbers of the circles. So if we start at 440, we're going to apply like the same formula. We're going to take the 440 times 2 to the power of, but this time n is going to be 0 to 360 instead of 0 to 12. So we start at 0, then divided by 360 instead of divided by 12. So I'm going to do the same thing, except I'm going to start at the 440. We're going to draw a circle around it, like our compass around it, but I'm going to draw 360 points instead of 12 points to our circle to have a full 360 degree circle. So if I do that, then I come up with this series of numbers, right? So now I have 360 points that all land on the circle. So now I can come up with, hopefully get to these same 12 numbers by doing an equal spacing here, but this time I have 360 degrees, and if I equal space that out to 12 notes, I come up to a nice even 30, right? So now I can equally space this every 31 and take the hertz. So if I do that, then I'm going to say I start at 440, and then my next note is going to be plus 30, 0 plus 30. So then I'm going to find this 30 down here. So 30 is going to give me that 466. So now we have an equally spaced bit here, 466. And then my next note, note number 3, is going to be 60, which is 30 plus 30, 60. And that will be 493 hertz. And then we go to the 4th, would be 60 plus 30 would be 90, and so on and so forth. So now we have our 12 notes, and we've once again mapped out these, which hopefully should come out to the same that we did over here for the most part. Right, 3, there's rounding errors, 7, 48, right? But it's pretty close. It's close enough to map onto our color wheel, right? So that's the general way that we get our 12 notes, which are measured in hertzes, which is what you'll see when you actually, like use a tuner. So that's going to be then our notes. If I apply the notes, it would be A and then A sharp or B flat, which I'm going to represent as a lowercase a, B, B, C, and then C sharp or D flat, D, D sharp or E flat, E, F, F sharp or G flat, G, and then G sharp or A flat back to A from a circular standpoint, noting that this A is going from 440 to 880 for our 12 notes, which is kind of like the middle point, right? That's where we kind of like the middle part of the piano, even though they start calling the middle C from the point of the C instead of the A, which again is a little, it's a little frustrating that they do that. Okay, let's say that we wanted to go up another octave. So now we've bent this into a circle. That's great because I can do the same thing with color. So now I can take the color spectrum, and even though color doesn't naturally repeat when you look at hues, we could still force it into a circle, and that will give us the analogy that we have here. So then we can start looking at our intervals here and looking at the equivalent intervals in color and come up with the associations of how the color maps, and that'll help us again make different connections in our mind, which will help us better understand both color and music, although our focus of course here is on music more than color. What if we went another octave up? Well, if we went another octave up, so now if you're thinking about the piano, instead of like in the middle of the piano, we're going up in pitch towards the right side, another octave up. It's repeating. So it repeats at 440 times 2, which is 880. 880 times 2 is 1760. Now you might note that we have a lot more wavelengths happening between the higher pitch octave, right? There's a longer distance in terms of wavelengths between 880 and 1760 and between 440 and 880. But our ear perceives them as in essence the same. You can think of like the ratios being in essence the same. So from our perception, there's like an equal distance, even though the number of waves is way higher when we go up. Okay, so that's interesting. But if I was to go one wave by one wave all the way from 880 to 1760 and count them from one, how many waves would that be? That's going to be a lot, right? We're going to go, okay, that's going to be way over 360. So see, the last one was like 400 and something. So this, if I do it one at a time, it would be going up, it would be 881 measurements. So again, that's not going to fit into 360 into a circle if I do it just like one by one, because 880, like if I took 880 by 12 divided by 12, I get to 74. So if I tried to do equal spacing, just look at the distance between that octave, it would be 880 units divided by 12, so I can do equal spacing, and I can say, okay, then I'm just going to take the 1, and then at we'll say 0, and then if I go up to the next one, it would be 73 about, because we round it down. So 73, and if I look up 73 over here, 73 units, that would give us 952 Hertz. And then if I go up equal spacing again to the next one, it would be 73 plus another 73 about, which would be 146. And then and that would give us then 1025 Hertz and so on. So if we did it that way, you would think this would be the Hertz for the next octave up, but that doesn't match because these Hertz are not always going to be double the starting Hertz. This one is, right? But because I started at 880, but that's not an equal distance for where we left, but all these Hertzes won't be double what we started at. It doesn't work, right? Equal spacing doesn't work. So what do we have to do instead? We've got to do the log thing, they call it, right? Force it into a circle, right? So we do the same thing. We could say if I start at 880 and I force it into a circle, this time I'm just going to do it for the 360 circle, not for the 12, and then we'll derive the 12 notes. So we have the same formula. So we're going to take the starting point of 880 times 2, because it's going to double, and then we're going to take that to the power of each of the units, which we're going to have 360 of them, divided by 360. So that'll force it into a circle if I do that on each of these 360 points. So then we're going to get our hertzes. These are 360 hertzes, which now I can equally space once again because we have a nice 360 units. So now we can take the total units is 360 divided by 12 is going to give us the 30 spacing and the next octave up. So if I started here at 0, we would be at 880. And then if I go to 30, we would be at 30, which would be 932. So in other words, if I went up to 30, that's now 932. And so then we're going to say, okay, if I went up again, the next one is going to be 30 plus 30, which would be 60, and that's going to be 988. And this would be an A sharp or B flat, and a B. And then the next one would be 4, which is going to be a C. That would be 60 plus 30, or 90, which comes out to hertz of 1046, and so on and so forth. So this would be the next octave up, which you can imagine to the right of the middle of the piano, in essence. But again, the piano measures it C4 to, measures it starting at C, calling it C4. We'll talk about that later. I think that's another area where they used a system that is not quite right? I would like to say the middle of the piano starts at 440 to 880 is the middle point, and instead of calling it a 4, like a C4, why would you call it a C4? You would call it a 0. That would be the 0 bit of your number line, so you can go 2 octaves to the right, 2 octaves to the left, right? Why did they use a 4? Because they didn't want negative numbers, I think, is the only reason. I don't like it. It doesn't. Why would it be? Anyway, we'll talk about that later. But that's the idea. Now, so why did I go through all this to play the piano? Or to play the guitar? Because now what we want to do is map on the color on top of this. We can do the same thing with the color wheel, and that will give us absolute colors, and the distance in color is represented by the distance in the wavelengths, which is analogous to the distance in sound, which is the number of waves that happen within the time interval. So we can get a similar analogous distance, and we can also start to see it as a wheel. And if we think about the opposite sides of the wheel from color, we can also tie that into 2 opposite sides of the wheel for pitch. What does it do? What does it sound like when I have 2 different sides of the wheel? And then I can associate that to the 2 different sides of the color wheel, right? That's how the association of the color will give us more than just using color randomly and just kind of randomly assigning a color, which isn't a bad thing to do, but it'll give us a lot more nuance and using the color a lot more efficiently if we visualize the color as a wheel that ties into the pitches as a wheel. And then we can also add depth to the color by adding the dimension of lightness. Okay, so that's what we'll do. That's what we'll do next.